So hello and welcome to our very first Phys 121 lecture. Let me just say that first off, I love physics. I'm a super physics geek and I love this course and I really hope you're going to get a lot out of it. So in this first lecture, we're just going to make some introductory comments on, the nature of physics, what a solution to a physics problem, should look like, and, a really, really important tool for you guys in solving physics problems, the idea of dimensional analysis. So let's just start with the nature of physics. So nature of physics. Okay, so I think the very first and most important thing to say is that the universe is deeply mysterious. Okay, so, we've had, physics proper, started around, 1600s or whatever with guys like Galileo and Newton and on and on. And since that time, we've unraveled a number of mysteries about how the universe works, how nature gets things done. And it turns out, though, that every time we unravel a mystery, we reveal a deeper mystery. Okay, so, first of all, Newton figured out, motion and calculus and, force causes acceleration, et cetera, et cetera. So we had the basics of motion. Nowadays, that was a mystery and then that was solved or unraveled. And then, nowadays we have mysteries like, just the very existence of space itself. Is space a fundamental thing, or is space emergent from, let's say, quantum entanglement, something like that? So the point is that as we unravel mysteries, the mysteries keep getting deeper and deeper. And certainly the universe is way more mysterious now than it was, say, for instance, in Einstein's time. Okay, so how do we unravel these mysteries? What's the actual process? Well, it's a two-pronged process. So on the one hand, physics is deeply rooted in experiment. Okay, so physics is an experimental science. We can come up with all kinds of crazy ideas about how the universe might be, all these kinds of guesses and so on. And but at the end of the day, if it doesn't agree with experiment, it's wrong. Okay, and so that's a famous line from Feynman. Okay, so so physics is definitely rooted in experiment. Okay, and then but at the same time, there's also theory. We have all kinds of models. Say the model of the atom. The first model of the atom was a plum pudding model, and then other models and so on. Eventually, we ended up with a quantum model of the atom. So we construct theories or models, guesses for how we think nature might be, how we think nature might be working. So this is we construct theories or models. Okay, and there's a very important interplay between these two. So for instance, we have a theory. So this is a mathematical model for how something is. We say, well, if this is true and this is true, then, mathematics theory tells us that something else must be true. And the best case scenario is when it comes up with a really interesting prediction that no one would have ever guessed. So theories and models come up with predictions for what we should observe by doing experiments. And so the theory comes up with a prediction, and then we subject that prediction to an experiment. So theories have predictive power. And when we do that experiment and we find out that, the experiment verifies that prediction, it does not prove that the theory is right. All it does is it gives us some additional confidence that we're on the right track with the theory. You can actually never prove any theory to be right. But you can prove it to be wrong with a single experiment. Okay, so when predictions agree with experiments, it increases our confidence in a theory. And when something is called a theory in physics, what that means is it has been subjected to all kinds of experimental tests, every single test we can possibly imagine doing on it, and it has passed all those tests. It still might not be right. It still might not be how nature actually works, but it's the best thing going, and it's a very good thing. Okay, so theory is actually a very powerful thing. So don't be caught saying, oh, that's just a theory. Okay, theories are very, very powerful things. Okay, and so then you do this experiment, and then, maybe the experiment shows that, that the prediction is wrong. So experiments have, corrective power, or, corrective is a good word. Okay? Or you do an experiment of something just totally out of the blue. Some surprising result happens, and you have no theory to explain that. And so then, experiment then gives rise to, ideas. Makes the theorists go to work and try to explain that new and unexpected experimental observation. Okay, so I want to give you sort of two examples of this. So I'm going to give you an example of this process here, where we started with a theory and it made an interesting prediction, which we then tested by experiment. Okay, so let's see. So let's do that one down here. Okay, so let's start with the theory. So the theory in question here is back in 1905, Einstein had figured out special relativity, which is a theory of space and time without gravity, so without mass, just flat space-time. And by about 1925 or so, people had sort of figured out the basics of quantum mechanics. And then Paul Dirac came along, super brilliant theoretical physics guy, little eccentric, interesting guy to look up. So he combined these two together. He said, if this is true in nature and this is true in nature, then it should, by mathematics and logic, it should be true that we have this relativistic field theory, quantum field theory it's now called. Okay, so basically, if this is true and this is true, math tells you that must be true. And this quantum field theory makes interesting predictions. So one of the really interesting predictions that it makes is the following. So what we're going to imagine is, I'm just going to draw a diagram here, and then we're going to talk about what that diagram means. Okay, so we have an axis, there's a time axis, t here, and there's a space axis, let's say x here. And this is a point on the x-axis, point A, and this is a point on the x-axis, point B. And this is a point C. Okay? And what we're going to imagine is a diagram like this. So there's a line which, say, goes up like this. And then there's a little squiggly line which goes like that. And then a line which, say, goes down like this. Okay? And we put arrows on this line. An arrow this way, an arrow this way, and an arrow this way. This is an example of a really sort of basic Feynman diagram, called the Feynman diagram. So the idea here is this line here represents an electron, so a negative charge particle. That's a minus sign there, negative charge particle. And what it does is it starts at point A, and it just drifts across to point B. So it just moves to the right like this to point B. It moves along the x-axis from point A to point B as time goes on. So it was at point A at this earlier time, and then it drifted along from A to B, and it ended up at point B at this later time. That's a later time, that's an earlier time. Okay, and so we say, yeah, great. So this is an electron moving from point A to point B, no big deal. Okay, and then at point B, something interesting happens. This little squiggly line, it represents a photon, a particle of light, which is emitted, and it just takes off to the left, going from B back towards A as time goes on. Okay, so that's all fine and well. But then we come across this line. So quantum field theory, just the math, predicts that this sort of thing could happen. But what does this represent? It represents an electron that moved, as time went in the forward direction, it moved from A to B. But now it moved from B to C. However, it started at point B at a later time, and it ended up at point C at an earlier time. So this line represents an electron moving backwards in time. Okay, so as a sort of physicist, you should think, ooh, wait a minute, that could be problematic. There could be grandfather paradoxes. There could be all kinds of stuff going on. That's bad. This violates causality. Okay, so that's an extremely important point here. So this violates causality. Now, causality means cause and effect. Okay, and so that is a pretty fundamental and cherished sort of principle of physics. And so this diagram violates causality. And so you scratch your head and say, is something wrong with this, this quantum field theory? Or can we be clever and creative and figure out a way out of this dilemma so that we don't violate causality? And so then you think for a second and you say, well, let's see. Negative charge moving from B to C is the same as positive charge moving from C back to B, right? Like when you have electric current, electrons flowing this way means the current is that way. It's the same as positive charges moving that way. Okay, and so then you just say, well, let's not think of this as a negatively charged particle, an electron, moving backwards in time from B to C. Let's think of it as a positively charged particle, a particle with exactly the same mass as the electron, but the opposite charge, a positive electric charge. And it's not moving this way, it's moving this way. Okay, so then this just says, oh, all that's happening is we have an electron moving from A to B, and we have its antimatter particle, a positron, moving from C back to B. They come together, they annihilate, they disappear, they're no longer there in the future, and what has appeared in their place is a photon. Okay, and so in order to not violate causality, we invent the idea of antimatter. Okay, and so it's fair to say that quantum field theory predicts the existence of antimatter. That's super surprising. That no one saw that coming. That was just like, whoa, what? And then, of course, you run the experiment. That can't be true. So then you run the experiment and you find, oh, yes, in fact, it is true. Okay, so you look at particles decaying in a cloud chamber, and you identify, oh, look, there's a particle with exactly the same mass as the electron, but positively charged. Okay, and so hence the discovery of antimatter. So that's a great example of a theory like these two guys here. You work the theory, you do the math, you get a new theory. This new theory makes interesting prediction like this. Okay, and it predicts antimatter, and then you observe and you say yes. Now remember, that doesn't prove that the theory is correct, it just gives additional support for that theory. Okay, let me give you another example here of this process. Okay, where we have an interesting experimental observation that is sort of out of the blue, and it leads to a new theory. So this will be number 2 here. Okay, so number 2 here. So we know that Newton came up with his laws of motion, F equals ma, and he also came up with a particular kind of force in nature, a fundamental force, gravity. And so we had this law, F is equal to G m1 m2 over r squared. It's a centrally directed force between all pairs of particles, blah, blah. And so that ended up with a way to predict the motions of the objects in the solar system, the planets in the solar system. Okay, and so that theory made what seemed to be correct predictions for a long time, for a couple hundred years. But then, in around the 1850s, mid-1800s, telescope technology had improved to the point where when you observe, say, for instance, the motion of Mercury around the sun, you find that it does not agree with the predictions of Newtonian mechanics and gravity. Okay, so what happens is, if this is the sun, and this is, say, Mercury over here, and what Newton's theory would predict is, if there's no other planets in the solar system, what it would predict is that Mercury should go on an elliptical orbit around the sun, like this, and when it comes back, it'll retrace its steps over and over and over again. Okay? But now you add to that the other planets in the solar system, and they exert gravitational tugs on Mercury, and they disturb its orbit. And the nature of the disturbance is like this. Okay, so Mercury comes around like this, and it doesn't come back to exactly the same point with the same velocity. It comes back a little bit different point, different velocity, and then it takes off like this. And so the orbit kind of does this. So you see that it's an ellipse. It has a major and a minor axis, and you see that the major axis started out pointing in this direction, ended up pointing in this direction. So over time, the major axis, the direction in which it points, precesses. It goes around like that. Okay, and so you do detailed calculations, and you find, yes, we should find that Mercury should precess a certain amount due to the effect of all the other planets. But then what you discovered was, when telescopes became really, really precise, you discovered that, oh, wait a minute, it doesn't quite precess the right amount. There's a slight discrepancy. It should precess this amount, but it precesses only this amount. And this discrepancy was very, very small. It's 43 arc seconds per century, per 100 years. Okay, so an arc second is, take 1 degree in the sky, 1 degree, and divide that by 3,600. So that's a very small degree. Okay, so 43 of those tiny arc seconds, you have to wait for 100 years. Mercury going round and round and round and round like this, and you'll see a super tiny shift or precession of the called the perihelion of Mercury, the major axis of the ellipse. Okay, so that's a problem. So how do you explain that? Well, one possible explanation is, maybe there's some other object in the solar system that we're not aware of. So people invented this idea of Vulcan, okay, and maybe Vulcan orbits around here. Some people claim to have seen Vulcan. There is no Vulcan. Okay, so at the end of the day, what happened is this was explained. This discrepancy, this surprising experimental result, was ultimately explained by a new theory, and that is Einstein's general theory of relativity, which is his model of space, time, and gravity, warping of space, time. And so, so that's kind of a really interesting point, because this is an extremely tiny discrepancy between experiment and theory. And so you might think, oh, well, the theory just needs a slight little tweak. And sometimes that's the case. But sometimes it's the case that the theory needs to be completely changed. Okay, turned basically upside down. You need an entirely new theory of an entirely different nature. And that's what happened with general relativity. So I'm not going to get into general relativity. We don't have time. One of my favorite topics. It's one of the things I do research on. But anyways, what I will do is I'll tell you one thing. I want to characterize how different this new theory of gravity was to explain this tiny little discrepancy compared to the old theory. Okay, so I'm going to ask you a little question here. So I have some notes here because I tend to go off on tangents, so I need to keep myself on task here. Okay, so I'll ask you a simple question here. So I'm going to show you a diagram here. We got a tree. This is like the Newton apple kind of tree. Okay, here's our tree, and it's sitting on the ground here. And in this first picture, we have an apple, which has fallen from the tree. So it's fallen down, okay, to the ground. And in this second picture here, we have the same tree, and we have the apple sitting up in the tree, attached to the tree limb, okay, and there's the ground. And the question is, in which of these two pictures is the apple accelerating? Is the apple accelerating in this picture, where it's falling down, or is the apple accelerating in this picture, where it's stuck to the tree? Okay, so Newton would say, yes, of course. Newton would say, well, of course, the apple is accelerating in this picture. Okay, and so you can see it's picking up speed. Okay, and so it's accelerating down. Well, Newton knew F equals ma, he figured that out. So if there's an acceleration down, there must be a force down. Okay, and so then Newton invents this idea of, oh yes, there's a gravitational force. The mass of the Earth must somehow be pulling on the mass of the apple, exerting a downward force, causing a downward acceleration, and yay, that's the explanation. Okay, and then this leads to, this prediction. Okay. But then that prediction turns out to be wrong, and so we're looking for a new model for gravity, for this reason and other reasons, actually. Okay, so then Einstein comes along and says, no, Newton, you have it completely wrong. It is in this picture. It is precisely in this picture that the apple is accelerating up. And in this picture, the apple is not accelerating. Okay, and so why is that? So this is a beautiful, beautiful thought experiment from Einstein. Okay, so what you do is you look at this situation and you say, well, that situation is equivalent to, usually three lines like that means equivalent to. So is equivalent to the following situation. Take that apple and that chunk of ground and stick it inside a rocket ship. Okay, and so here's our tree, and here's the apple stuck to the limb of the tree. And what we do is we put rocket thrusters down here and we blast them so that the entire thing is accelerating up. Okay, and let's make it accelerate up with a magnitude of acceleration g. In this situation, I want you to think about this. I want you to imagine yourself standing here. What do you feel? You feel gravity pulling you down, okay? And when you drop something, it accelerates down, etc. Well, imagine that you are in this situation where you're out in the middle of empty space, there's no gravity around, and the box you're in is accelerating up. Okay, you're going to feel exactly the same thing. You're going to feel pushed into the ground. When you drop something, it will appear to accelerate down, etc., etc. Give that some thought, okay? So anyway, so then Einstein said, no. What's happening is this situation is physically equivalent to this situation, okay? So really what's happening is and how does that work? Well, that gets complicated. So you get into the idea that the mass of the Earth does not exert a force on objects pulling down. What the mass of the Earth does is it warps space and time. Okay, inside the Earth and above the Earth, around the Earth, it warps space and time so that time moves more slowly the closer you are to the surface of the Earth. Okay, so that change, time moves more quickly up here than down here. And it turns out, if you do a little bit of math, you can figure out that that's physically equivalent to this situation of accelerating up. Okay, so actually, in this situation, the ground is accelerating up without going up. Okay, and so this is a completely radically different picture of what gravity is. And that radically different picture was required to explain this, but then many other things. Okay, so then this radically new picture of curved space-time kind of gravity, it makes tons of predictions. It predicts things like, expanding universe. It predicts things like, which of course was observed by, Hubble. It predicts things like black holes. Okay, and so that, we now have direct evidence. So one of the people in our department, Avery Broderick, he was on the Event Horizon team, one of the key members, where they, first put together a millimeter wave radio telescope, basically the size of the Earth, and they imaged for the first time a black hole. So that's the most direct evidence we have yet for a black hole. So this is, and another is gravitational waves. So the LIGO project. Gravitational waves were predicted 100 years ago. It took 100 years to develop the technology to be able to actually measure those gravitational waves. So these are very deep and profound predictions of general relativity, this new model of gravity. So it's like this, predictive power, okay? All kinds of weird predictions that you would have never guessed. And all of them so far, dung, 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 and many more, have turned out to be true as far as technology, human technology exists today. Okay, so anyways, yeah. So that's basically it. So I wanted to just give you a feeling for the nature of physics. The universe is deeply mysterious. We are nowhere near having resolved all of its mysteries. And the process by which we do those mysteries is sort of hand in hand, or these two, experiment and theory, work hand in hand. It's like two sides of the same coin. That's why you take a lab course, and that's why you take the 121 more theory course, because the two of them work hand in hand. It's that process which unravels mysteries. And as we unravel mysteries, we always get to deeper and deeper mysteries. So, what awaits you in the future, if you stick with physics and you work hard, is, you can really see how amazingly beautiful and deeply mysterious our universe really is. There's lots of stuff to still figure out, way more than there used to be. Okay, anyway, so that kind of concludes this sort of part of the first lecture.